right. Hello. Thank you, everyone. Thank you for your patience and welcome to this quick Quake Briefing webinar on the 7.4 magnitude earthquake that struck Taiwan in April of this year. My name is Elizabeth Angel. I'm EERI's Communications and Program Manager. And for those of you who aren't familiar with us, I just want to take a quick moment to introduce you to EERI. We're the leading nonprofit organization that's dedicated to connecting professionals from a wide range of disciplines and backgrounds, both here in the US and around the world, who are working together to better understand earthquake risk and advance earthquake resilience. So you can find out more about us at our website. We'd love to have you join and become part of the work we do. This webinar is the first in a series of 2 webinars. The second is scheduled for September 19th. But this webinar is hosted specifically by the Northern California chapter of EERI as part of their Quake Briefing series. So I'll turn it over to Richard McCarthy, who's the president of the Northern California chapter, to welcome you.
Well, welcome everyone. Thank you to our guest from Taiwan. We're looking very much forward to your presentation. We're the Northern California chapter, and we focus on earthquake engineering, seismic policy, and other issues, as Elizabeth mentioned. We're particularly happy to have our partners in Taiwan because we learned so much from your experiences. I've had many trips to Taiwan and made many friends there. So I'm going to turn it over to Bruce to introduce our first guest. Bruce, would you take over, please?
Oh,
Bruce, you're on
your
mute.
microphone.
There you go.
Okay, welcome to our briefing on the magnitude 7.4 earthquake that struck Taiwan earlier this year. My name is Bruce Mason. I'm one of the executive board members for the Northern California chapter. Our briefing series is a free series open for anyone to view. This is our 4th briefing this year. We had 2 earlier on the Japan magnitude 7.5 earthquake, the Noto Peninsula earthquake, and we also had one on the magnitude 4.8 earthquake that was centered in New Jersey but affected New York City. Now, if you're a member of EERI, you will get email notifications of the upcoming webinars as we develop them. However, if you're not, you can still get on our mailing list. And how you do that is send me your name to the address shown on this slide, and I will put you on our list. Now, on to the Taiwan earthquake. The recent earthquake in April was the strongest earthquake to affect Taiwan since the 1999 Chi-Chi earthquake. This earthquake damaged about 3,000 buildings, but there was remarkably few collapses. There were power and water outages. There was about 800 landslides, and these landslides were the main contributor to the fatalities that were caused by this earthquake. There was even a small tsunami occurred. It had about a 1-meter wave height. So this earthquake was a significant earthquake. And today we are excited to have 2 outstanding speakers from the National Center for Research on Earthquake Engineering in Taipei. One of our speakers will talk about the seismology and the strong motions recorded during this earthquake. And the other speaker will talk about the effects on the built environment. Here's the format for today's program. It's about a 60-minute program. Each of our speakers today will talk for about 20 minutes each, and the remaining time will be for question and answers. Now, we encourage questions from the audience, and how you will do that is you will press the Q&A button that you see at the bottom of your screen, then type in your question. Then behind the scenes, Elizabeth and I will go over the questions, and I will come back later in the program and pose the questions to our speakers. Now, we know there might not be enough time to answer all your questions, so each of our speakers has kindly provided their email address, and it'll appear in their presentation. And so you can send questions directly to our speakers, and in the coming days, They will try to answer your questions. Now, what I would like to do is introduce our first speaker. And I believe we'll go with the Dr. Lin, because I believe he's on the screen now. Because of the technical difficulties, we thought we might have to switch the order. So our first speaker is a Dr. Lin. He's a senior research fellow at the National Center. He will be talking about the seismological aspects as well as the strong ground motions recorded during this earthquake. Dr. Lin, can you please proceed?
Thank you, Bruce. Okay, let me share my slides. Okay, can you see my slide?
Yes, it looks good.
Okay. Okay. Hello, everyone. Thank you, Bruce, again. And I will try to provide you the background information about the source and strong motion of the large earthquake that happened on April 2nd this year. I hope after my presentation, it may be easier to understand the causes of the earthquake damage that Director O will present. Well, at about the end of the April 2nd, an earthquake with a magnitude 7.4 occurred in Hualien City in eastern Taiwan. The local time about 8 o'clock in the morning on April 3rd in Taiwan. And the left side is the earthquake report announced by the Central Welfare Administration, CWA, in Taiwan. And the right side is that of the USGS. And considering the data resolution and integrity here, we will mostly use the data of the CWA. So based on the CWA report, the epicenter of the main shock was located onshore in Hualien. And here, the focal depth is about 22 kilometers, and the local magnitude is 7.2. Actually, the original epicenter was located in the offshore region, and the CWA recently renewed the locating result. The epicenter was moved to the onshore region west of the original epicenter, and the focal depth also became deeper. Okay, the strong ground motion of the earthquake reached the CWA intensity of 6 plus at the region of Hualien County near the epicenter. This means the near field region experienced a PGV, peak ground velocity, of over 80 centimeters per second. And the intensities of most of the northern half of the island reach 5 minus. This means that the peak ground velocity is over 15 centimeters per second. And the peak ground acceleration is over 80 gauge. And the definition of the CWA intensity is shown on this table here. So before briefing you on the earthquake, I would like to remind you of the regional information on the seismological tectonics in Taiwan. The Taiwan Island was formed by the convergence of the Eurasia Plate and the Philippine Sea Plate. And the Philippine Sea Plate moves to the northwest with a velocity of about 80 millimeters per year. And the Eurasian plate is subducted to the north as to the west, and to the east at the south of the island, and at the northeastern of the island, the Philippine Sea Plate is subducted to the north. Sorry. let me use. Okay, it's better. At the northeast of the island, the frequency play is abducted to the north. So the longitudinal valley in eastern Taiwan here is a suture zone. It's the boundary between the Eurasian plate and the Philippine Sea plate. So most of the Taiwan island at the west of the longitudinal valley is seen as the front of the Eurasia plate. And only the coastal range at the east of the longitudinal valley belongs to the Philippine Sea plate. And along the boundary between the longitudinal valley and the coastal range, there is a series of long faults called the longitudinal valley fault system. So many disasters, earthquakes were related to it. So the fault tracks on the ground are clear and well identified. And it is dominated by the eastward dipping thrust or the strike slip structures, including several active faults. And recently, however, the existence of another westward dipping fault on the west side of the longitudinal valley has become certain by surface geology and seismicities. It is called a central range fault because it is the boundary between the central range and the longitudinal valley. Here we revert to the model of the Huang and Wang 2022 based on the 3D velocity model and the relocated earthquake hypocenters. In south of the top of central range fault is beneath the longitudinal valley fault, but in the north, the central range fault truncated the longitudinal valley fault, separating the northernmost longitudinal valley fault into a shallow and deep segments. Therefore, the shallow structure in the northernmost become complicated. So because of the tectonic background, the eastern Taiwan has extremely seismicity. This figure shows the historical earthquake since 1900. The blue circles are earthquakes with a magnitude larger than 6. The number is about 100. The epicenter of the April 2nd earthquake is the red star here, and the red the red circles are some significant earthquakes before 2000, and the largest earthquake in this region was happened in 1920 with a magnitude of 8 here, and in 1951. 5 earthquakes of magnitude about 7, including here, and here, consecutively shocked this region between October and November. And they seriously damaged the region from the north to the south of the longitudinal valley. And then the earthquake with a magnitude 7.3 happened in 1986. It caused not only the damage in Hualien, but also building collapse in Taipei in northern Taiwan. After 2000, there were also several earthquakes happened and caused some damage in eastern Taiwan. The magnitude of them were mostly less than 7. Okay, let's come back to the April 2nd earthquake. After the main shock, a great number of aftershocks occur, 7 of them have a magnitude larger than 6. And this figure shows the distribution of the aftershocks until the end of April. And the colors are the depths of the aftershocks. We can see that the aftershocks occur on a linear region with a length of about 70 kilometers along the northeastern strike of the local structures. And their focal depth vary from 10 kilometers to 30 kilometers. And this figure is the time series of the aftershocks. And this is an animation to show it. After the main shock, many earthquakes immediately occur and extend to the northeast in various depths. After the first wave of aftershock, a second wave began on April 22nd. Here you can see with 3 large ones, and they concentrate at the source of the main shock and were shallower than 10 kilometer deep. And furthermore, a minor third wave with 2 large earthquakes start on April 26. After the aftershocks have continued to occur until now, and actually this Monday, a magnitude 5.5 earthquake occurred around this region. Here we show 3 depth cross-section profiles of the earthquakes. Here, A profile, B profile, and C profile. And it is clear that the main shock here ruptured a high angle and east dipping fault plane from a depth of 10 kilometers to 30 kilometers. And the fault plane extends to the northeast. And in the northernmost part, the widely distributed earthquakes suggest the complex structure of this area. And besides the second wave, aftershocks south of the main shock, what we just mentioned are concentrated here. It may be a shallow fall triggered by the April 2nd earthquakes. Here we show the focal mechanisms. The focal mechanism of the main shocks announced by different organizations and methods are all similar. And they all suggest that the main shock was a thrust fault with northeast-southeast strike. It agrees with the east dipping rupture plane represented by the aftershocks. And however, the focal mechanisms of the large aftershocks are apparently different. And it may result from the local rupture or trigger fault. Here we also show the historical moment tensor solutions in Taiwan as a reference. And there are here we show 2 results of the source rupture inversion by the final fault method, which are from the Dr. Lee from Academia Sinica Taiwan and the USGS. Actually, the results are highly similar. The maximum slip of the fault plane happened near the hypocenter of the main shock. And the large slip moved to the shallow part in the north. And most of the seismic energy was released within 20 seconds, but the rupture duration was over 40 seconds. And the thrust fault rupture of this large earthquake along the northern longitudinal valley fault is also presented in the co-seismic displacements measured by the GNSS stations around Taiwan. And the stations on the hanging wall east of the longitudinal failure fault have the largest uplifting of about 40 centimeters. In horizontal, and the stations on the footwall west of the longitudinal valley fault relatively moved to the southeast with the largest displacement of over 20 centimeters and push the eastern side displaced to the north and south. Back to analysis the strong ground motion of the Hualien earthquake. The records of about 660 free field strong motion stations operated by the Center Weather Administrations and NCREE were collected. And here are the three component acceleration waveforms recorded in Hualien, the near source region, and Taipei of northern Taiwan. And this maps shows the short time peak accelerations at all stations for every second. And we can see the propagations of the seismic waveform with time, and even the final acceleration of the surface wave in Western Taiwan. And the PGA recorded at each station is shown here. A maximum peak ground acceleration of 1.5 G was observed at the Taroko National Park. The shape map of the peak ground acceleration shows that there were large areas that experienced ground motion of over 400 gale in eastern Taiwan, and about half of the island was shaken by the ground motion of over 80 gale. For the ground velocity, the maximum value observed near the epicenter was over 80 centimeters per second. The high peak ground velocity region extended from the epicenter to the north. And the peak ground velocity of the island's northern half is higher than of the island's southern half. Here we also show the shape maps of the spectral acceleration of 0.3 and 1 seconds. The distribution of the short period and long period spectral acceleration is similar to the PGA and PGV maps. The area with high short period spectral acceleration is large around the epicenter, but the area with high long period spectral acceleration is narrow and extend to the north along the coastal line. Besides, some local places show relatively high ground motion, especially in northern Taiwan, like the Yilan Plain, Taipei Basin, Taoyuan, Hsinchu, and Taichung area. Here we show some near field strong ground motion. This is the three component acceleration waveforms with the maximum peak ground acceleration of 1.5 G. It was observed at the Taroko National Park here, which is about 60 kilometers away from the epicenter. And there is a clear peak in the two horizontal waveforms. And the horizontal response spectra at the short period is extremely high and even beyond the design earthquake of the Taiwan building code. And the ground motion of another station at the Heping village here is also shown here. The difference is that it presents a high horizontal response spectra at a period of about 1 second. And between the Taroko National Park and the Heping Village, the high intensity and long duration ground motion of the Hualien earthquake induced a lot of large scale landslide. And these landslides caused the most of the deaths during the earthquake, and heavy damage to the national park and the main traffic arteries. These two ground motion were observed in Hualien City and Shoufeng Township, which are close to the epicenter, and they have the higher population and more building structures. The peak ground acceleration observed there was about 500 Gauge, and the response spectrum was beyond the design earthquake of building code. So most of the building damage and even the building collapse were located in this ridge area. Besides the near field ground motion, we would like to discuss the local implications in northern Taiwan. The ground motion in Yilan Plain, Taipei Basin, Taoyuan, and Hsinchu is relatively higher than in the surrounding area. The implications are clear when compared with the ground motion model. And some of the response spectra are close to the design code. And some buildings in these regions were partially damaged during the Hualien earthquake. And there are some reasons caused the seismic amplifications in these regions. The first one is, of course, the side effect. The site implications in the Taipei Basin and Yilan Plain are significant and well known from historical earthquakes. And the second reason is the long period velocity pulses. About a dozen stations observe the pulse-like velocity waveforms during the Hualien earthquake. Most of them are located at the Yilan Plain. The velocity pulses result in the high peak ground velocity and long period spectral acceleration in Yilan Plain. And finally, this is the comparisons between the ground motion predictions for the Hualien earthquake using the traditional ergodic ground motion model and non-ergodic ground motion models. The non-ergodic model reproduces the observed ground motion well, and the results suggest that the rupture directivity and dynamic radiation pattern of the source may contribute to the ground motion application in northern Taiwan. So this is my summary. The magnitude 7.4 Taiwan earthquake on April 2nd ruptured a high angle and east dipping fault plane with over 70 kilometers in length from a depth from 10 kilometers to 30 kilometers. It may correspond to the northern part of the deep longitudinal valley fault system. It is the boundary between the Philippine Sea Plate and the Eurasia Plate. And the high intensity and long duration ground motion of the main shock caused many building damage and a lot of large-scale landslides in eastern Taiwan. And the side effect, velocity pulse, source rupture directivity, and radiation pattern result in the local ground motion amplification in specific areas in northern Taiwan. Okay, thank you. This is my presentation.
Okay, thank you, Dr. Lin. I compliment you. Your slides were excellent. Your graphics was excellent, and you presented a lot of information. Thank you very much. Now, I would like to move on to our second presentation of today. This will be by Dr. O. He is the director of the Earthquake Center, and he will be talking about the damage or the effects on the built environment. So, Dr. O, could you please proceed?
Thank you, Bruce. I think I already shared my screen. Let me see.
Go to slide mode.
Okay. Okay.
Okay, that's the summary. Okay, very good.
Okay.
Oh.
Okay, so can you see
Looks
my
good.
slides?
Looks
Okay,
good,
thank you.
yes.
Thank you. It's my pleasure to present the damage to buildings and other infrastructures to you today. So I'm the director of NCREE, and I already put my email address on the slide. So if you have any question, that you can use this email to ask me after this presentation, after today's event. So this is my content. I will talk about the building damage, and also I will spend some time to talk about the performance of isolated building. And I will talk about geotechnical damage, although this is not very significant. And there was no damage to bridges, so I will not talk about the bridges. So first of all, it's about the building damage, and I divide the content into two parts. The first one would be talking about the low-rise buildings, and then the second part will be talking about the high-rise, mid to high-rise buildings. So, hold on a second. Let me try to close. Okay. So, before we talk about the building damage, I want to show you the acceleration magnitude of the ground motion. So you can see from the left-hand side, the peak ground acceleration recorded in the Hualien city is 458 Gale. Gale means centimeter per second square. So 1G is about 1,000 Gale. And on the right-hand side, you can see the response spectrum of the ground motions, including the north-south direction ground motion, and the east-west ground motion, and also the vertical ground motion. And let me see if I can you see my mouse? Pointer?
Yes, we can see it.
Yes.
Okay, yeah. So you can see that the response along the north-south direction is quite significant. The spectrum acceleration at the 0.3 second, it's about 1,400 Gale, which is even more than the NCREE design spectrum value, according to Taiwanese code. So the shaking was quite significant. In the east-west direction, the response of the acceleration is not so great like the north-south direction. And this is the vertical ground motion response spectrum. So if we normalize the spectrum value of the ground motions, this is along the north-south direction, and this is the east-west direction. If we normalize the spectrum value to the design spectrum value, the design earthquake spectrum value. So you see that for the north-south direction, between 0.3 second to 1.3 second, the spectrum acceleration of the ground motion are more than the design spectrum value. That's even 60% more than the design value. In the east-west direction, between 1 second to 1.2 seconds, a little bit more than the design value. So from this comparison, you can understand that the shaking was quite significant. It's more than the design spectrum value, more than the shaking expected in the design. So in the following slide, I will show you the damage to the buildings. So from the photo, you can see this is a collapsed building. The first story was totally gone. And this is a typical 12-week story collapse. And this building is a corner building. It's located in the intersection between two roads. So we believe that this building was easy to get some torsional response. So that's why we believe that maybe some of the columns were damaged due to this kind of torsional eccentricity effect. And this is another also corner building. We saw some damages to the building columns, and yeah, some spalling of concrete cover. And we found that from the design drawing that this building is supposed to have some walls in the back side, as shown here. But when we went to the building side, we did not see these walls. These walls were removed, probably due to the need for the space for the business. And so this removal of the wall weakened the building resistance to the earthquake. And this is also a corner building. And so we also found many corner buildings suffer quite significant damage in the first story. And some of them, as you can see, that they have a taller first story. And so these and also you can see that the walls, the exterior wall, was less in the first story compared to the other story. So this creates soft, weak first story, so easy to get damage, and because of the eccentricity due to the corner building, the irregular building plan. So it's easier to get the damage. So then we talk about the damage to the high-rise buildings. And so for high-rise buildings, because the periods are longer, so maybe we can look at the spectrum response around the 1 second. And you can see that the spectrum value greatly exceed the design value in the north-south direction. So I forgot to mention that for the low-rise building, we may check the spectrum response in the small period region, for example, 0.3 seconds. You see that the spectrum response of the ground motion also exceed the design value in the north-south direction. Okay, so let's come back to the high-rise building. So if we look at the 1 second spectrum response, it's significantly more than the design value in the north-south direction. And also in the east-west direction, the spectrum value of the ground motion, it's a little bit, it's also more than the design value. So these pose a a challenge to the building that we design, even based on the design code. We expect that some damage is expected. I mean, we expect some damage. And so this is probably the most famous building in the news. This building collapsed in the first story, second story, partially. And this building is a 10-story building. And yeah, it's also a corner building. And it is worth to mention that this building suffered some damage during the 2018 Hualien earthquake. Already some damage occurred to the building. And then the staff of NCREE went to the site, went to the building, and tried to persuade the building owner to do the seismic retrofit. But at the end, the building owner decided to do just the repair. They did not choose to do the seismic retrofit. And so this time, this building did not go through the earthquake. At the end, it collapsed. So we believe that if they, have chosen to do the seismic retrofitting, the result will be different. We have some other proof to show you the effectiveness of doing the seismic retrofit. So, and this is another, mid to high-rise building. It's 15-story high, and you can see some damage to the exterior walls, and also some damage to the second floor girder, but this is just one girder. Most of the damage only, occur in the exterior wall. And it is worth to mention that in Taiwanese practice, these walls, these are exterior walls with openings, are usually considered non-structural walls. They are not considered in the structural design, in the structural analysis. And so we expect that these walls would suffer damage during the design earthquake, like this one. So this is expected in our design. And we mainly rely on the special moment frames in this building to resist the earthquake. And this is another building, and you see that there is a setback in the third floor, and then so you see that some damage occurred. Okay, to the columns, and then also some exterior wall to the fourth floor and higher. And because I believe that this building was designed based on earlier code, so you can see that the reinforced detailing was not so good, so some field damage to the column also. And this is another building. You see that quite many, damage to the exterior wall, but no damage to the moment-resistant frames. And this is expected in the design. This one, I think that the first story is quite, weak, compared to the other stories. So there's some weakened and soft first story problem to this building. So a lot of damage occurred in the first story. And also we found that the construction was not so good, the quality. You can see that some longitudinal bar, were cut because they need some holes for the pipeline. This is not a good, construction quality. You see that this is one of the main bars cut, due to the pipeline during the construction in the first story. And this is a shear failure to one of the I think these two beams, two of these beams had a shear failure. And this is due to the short beam effect. You can see that this is the beam between the two columns, and these two beams are beams of spectral moment frames. But because of the presence of the RC wall, these are non-structural RC wall in Taiwan needs a design, and also some walls for the I believe these are elevators. So these walls make the beam much shorter than the original, so the shear demand increased. And that's why you see some shear failure in these portions of the beams. And we also found in the basement, some columns suffer a severe axial damage. And I believe that the detailing was not so good for these columns. And so a significant cracking of the concrete of the column can be observed. And this one, it's the columns of the pedestrian arcade. I think that from the damaged column, you can observe that the detailing was poor. You see left splices of reinforcing bars in the passenger regions. So this is not a good detailing, and so that's why you can see such severe damage to the column. So let's look at the performance of retrofitted buildings. This building was damaged during 2018 foreign earthquake. The magnitude was about 6 point something. And this building suffered some damage to the walls and the beams. And after the earthquake, the building was seismically retrofitted with the reinforced concrete walls, as you can see along these lines. And then during these years earthquake, no damage was observed to this building. This is another building suffered some damage during the 2018 foreign earthquake, and then after that, the building was retrofitted by wing walls. You see that we add the wing walls to this column, and also some walls to the column, and this time no structural damage was observed to this building. So another example here, after we add some walls and to retrofit you see the blue line, these are retrofitted walls to retrofit the building, and no damage was observed during this earthquake. This earthquake was larger than the previous one. And this building was retrofitted with the buckling restraint braces, and we just finished the retrofitting right before the earthquake, and no damage to the building was observed. And this one is another example, famous example. This building was also, even older than this collapsed building. This building was the building that I just mentioned that the building owner chose to just repair. And this building owner, they did some BRB seismic retrofit to the building and suffered no damage to the building. And this just right, next to the collapsed building. So this shows the effectiveness of the seismic retrofit. And this is another example. This is a school building, and this one without retrofit. This one is with the retrofit and no damage to the building. And this one, a lot of damage to the columns and the beams and the wall. And this one, well, after the retrofitting, we installed the structural health monitoring system. And then we found, first of all, no damage to the structure system. This is in the Taipei city area. And we also measure the acceleration and in fact the dispersion response. And the maximum acceleration, ground acceleration is about 86 scale. And the displacement, the relative displacement in the first story It's about 0.3%. This is lower than the 0.5% that is expected in the design during this type of small ground quake. So the performance of the building is consistent with the design expectation. So we have this statistical data to show you that the damage distribution of the buildings according to the construction year. And the red means that the building had a severe structural damage, so people cannot live inside. The yellow means that there's some damage to the non-structural component and people still can live inside. The green means no problem to the building. And you see that most of the damaged building are the building which were constructed before 2000. After 2000, the year of 2000, after we have a better design code to make sure that we have a good building, seismic design, you can see that the damage was much less. No red tag to the building constructed after 2000, the year of 2000. This shows that the modern design code are better than the older version to ensure that our building have a good seismic performance. So these are the conclusions of the building damage. And I think I already mentioned most of them, all of them. You know, so I will just continue. Okay. Then I will talk about the isolated building damage in the following slides. And so we inspected the 19 seismic isolated buildings after the earthquake. And the most important one is this one. This is a hospital building in the Hualien region. This building suffered the largest isolation displacement is about 500 millimeter. And the second important building is in the Yilan County because this region also suffered quite a significant ground shaking. The isolation displacement was 250 millimeter. And so overall speaking, there was no damage to the structure of these isolated buildings. Some minor damage to the cover plate to cover the gap between the elevator and the superstructure. You know, just some minor damage, you know, to this cover plate because of large displacement between the isolated structure and the ground. So the displacement was quite large, and you can see from this video. So the middle part, this part, is the ground, and on the two sides, these are the isolated structure. So I want you to watch the movement of this lady. This lady will walk into the isolated structure, and there is another there is a guard who landed on the ground. So I want you to you know, watch their behavior. So the taking started. You see that this lady was able to walk as usual because she was in the isolated structure, but this car cannot walk. He standed, he stood on the ground. So strong shaking. Yeah, we can see this again. So there was a very significant displacement, relative displacement between the ground and the structure. Okay, and this one shows you the recorded video of the isolation during the earthquake. This is the first time that we have this type of recording, the actual movement of a lead rubber bearing during the earthquake. You can see that the relative displacement was quite significant. And this is a isolation system that we put beneath our data center at NCREE in Taipei. And I will show you this is the isolation system, and this is the equipment. I will show you the victim during the earthquake. So you can see that the isolation was working and the equipment was protected. So you might wonder that still some displacement of the equipment. I will show you what happened if you don't have the isolation in the following slide. Okay, so this is what happened if you don't have the isolation to the equipment. This was recorded in Hualien. So you can see that the equipment was, severely shaken. Okay, so if we take this hospital, for example, this is in the Hualien city and suffer a very large displacement in the isolation layer, and they use a 74 lead rubber bearing and also some sliding elastomer bearing in the base to protect the hospital. This is the most important hospital in the Hualien city.
Excuse me, excuse me, this is Bruce Mason.
Okay.
What we'll do, it's already at our time, but we would like for you to continue, Dr. O, and we'll have to cut short the question and answer period. Your presentation is so good that I would like to see the rest of it. So please proceed.
Okay. I will try to accelerate my presentation. Yeah. So you can see that no damage to the structural part, and the equipment was also protected in the hospital. But because of large displacement of the ground, and so you see some damage to the cover plate, cover the gap between the structure and the surrounding ground. And you can see that this is the acceleration response spectrum of the ground motion. If we scale the spectrum acceleration response of the ground motion to the NCREE level, then you see that there are still a lot of significant component in the long period region. So we put the isolation to lengthen the period of the building, so that we hope that the acceleration, spectrum acceleration can be reduced. However, if you look at the spectrum response, of the ground motion, still we have a lot of response in the long period range. That's why we saw a large, relative displacement of this building during the earthquake. And the peak input acceleration for this building was about 200 Kel. And we have we have accelerometers installed to the building. So we know the response of the building. So this is the acceleration response of the building, and this is the isolation layer. And so these acceleration represent the ground acceleration, and these are the acceleration response of the building. So first of all, you can see that the period of the building was indeed lengthened, and the effective period of the building were about 3 seconds. So the isolation was effective to lengthen the period. However, because of the very significant long period, spectrum response of the ground motion, so still, we found that the acceleration reduction efficiency was not so good. We still have a quite significant acceleration response in the buildings. And also we can see that the large displacement occur. This is predicted because the displacement transducer was damaged in the previous earthquake. So we can only use the acceleration measurement to predict the displacement response. So even though the structural damage was minimal, to these isolated buildings, but we found that the isolation efficiency was not so good as we expect because of the large long period component of the near foreground motion. So this is something we need to pay attention in the design of the isolated building. Okay, so this one will be quick. This is about the geotechnical damage. Not so much was observed during this earthquake, only in the port area because of the reclaimed land and by the gravel and sand. So during the earthquake, there was a soil liquefaction found. You can see there's some sand boils and cracks, and also some subsidence of the ground. Only occur in the port area, not in the residential area in the city area. Okay, so this is my presentation. Thank you.
Okay, Dr. O, thank you so much for your presentation. Again, your graphics were excellent with much good information. Unfortunately, because of the technical difficulties, we had a late start today, and we're already 10 minutes over, so I will draw a close. We will not have the traditional question and answer period. However, the audience is welcome to send your questions directly to our speakers, and they will try to answer them in the coming days. Also, both of our speakers kindly will make available their presentations, and they will be posted on the EERI website. However, that might take a week or so. In their presentations, they will have their email addresses, so you can be able to send them questions at that time. What I would like to do now is end my part of the presentation today, and I'd like to turn the floor back over to Richard McCarthy to say a few closing remarks. Richard, could you please proceed?
Well, I agree with Bruce's analysis. These presentations were fantastic, some of the best. And thank you very much. The graphics gave us so much information, practical information in these presentations. And there's a lot of usable information here, and I'd like to get copies of these presentations as well. There's some graphics here that I could use in our legislature for sure, demonstrating the benefits of retrofitting non-structural issues as well. So to both of our speakers, thanks again very, very much. So I'll turn it over, Elizabeth. I'll turn that over to you.
Great. Thank you again, everyone, for attending. I'm sorry about the delay at the beginning, but I hope you found that as interesting as we did. I just wanted to remind folks that we have a second webinar in this series. It will focus on functional recovery. That's on September 19th at 4:30 p.m. Pacific. If you were registered for this webinar, you're automatically registered for that one too, and you should get a reminder email about that. So we hope you can join us for that one as well. There'll be a post-webinar survey on your screen when the session closes. You'll also see that in a follow-up email. Please fill that out if you have time. You can learn more about EERI at our website, join us, find out about upcoming webinars at those addresses here. And then finally, I just want to thank the people who make the work we do possible. This webinar series and EERI's other activities are made possible by our members and also by support from FEMA under a cooperative agreement. So thank you very much for joining us. Please do send your questions. Oh, and just about those slides, they'll be on the Learning from Earthquakes website. So learningfromearthquakes.org. And if you go on that homepage, you'll see a virtual clearinghouse for the Taiwan earthquake. So that's where you'll find the PDFs when we post them. We'll also put a link to the video of this webinar up there. Thank you again for joining us today.